Hello algorithmicians, this video is going to go through some questions for Unit 3 Outcome 2. You may have done these questions. Make sure you watch the video anyway. It may contain things that you will have got marks for, but you may lose in an exam, or it may contain better ways of doing things. So here we go. If you haven't seen these questions before, of course, try them pausing the video and then watching for the solution. Now we start out with this cheeky Dijkstra graph. Let's get the pen. And we're going to start from A. So A is permanent with a distance of 0. So we write A here for our order. And then from A, we can go to B and C. And the first one of these that we make permanent is C. So we put this in a box here and we write C down here. Now, a big mistake people could make is, well, two things you could do. You might first off go from B to D, but that's not what we do next. The first one we should be working from is C. And the other thing people might do is try either now or later to change the value of C. So the problem with Dijkstra is that once we have made a vertex permanent, it remains permanent. So from C, we can only go to D. So we'll add 3 to 3, which is 6. Now we look at B and D, and we choose B, being the smallest. So we write B, and then we can see that from B we can get to D using a slightly shorter distance of 5. So that is now our permanent shortest distance. So the order there needs to be A, C, B, and D. And the vertices, and you just get this by inspection, where Dijkstra produces the incorrect result. We can all see that C should actually be 1, so C is wrong. And because C is wrong, it means that D is also wrong, because, well, not because, but happens that we could do 1 plus 3 is 4 to get to D. Make sure we're stating vertices. I've seen some people sometimes write edges instead of vertices. So like saying things like A to C is 3, when really we want to know what C is. Okay. Moving on from here, Dijkstra cannot guarantee a correct result when negative edges are present, and so we can use either Bellman-Ford or Floyd-Warshall. Okay, moving on, using a damping factor, etc. This is going to be a bit of a brutal one, but let's go through. So the first thing we know is that we need to initialize our table of page ranks with 1 divided by n, so 0.25 for each one. 0.25. Bum, 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 bum. Now, we know we're going to have to do 2 iterations, so we're going to need 1 iteration of A here, and then we need to find this value here. And if you are being efficient, you can just find the ones that you need, so that we know that to find A, we need to know the page rank only of D, because D is a sync node which distributes to B, to A, and to C. Now, if you distributed it to D as well, last year, well, in the 2025 exam, that was allowed, but the consensus was it really should be only going to all the other nodes. Okay, going back to itself doesn't really model the problem very well. Remember, this is a random surfer, and we're saying a random surfer's got to D, they can't go anywhere else, so where do they click? Well, they're probably not going to click on D again. That would be, well, it wouldn't make any sense. We wouldn't just click on D, we would just read it again. So that means we need to know for D, and for D we are going to use the page rank. Where are we? Here we are. So page rank of D for number 1. So we have the damping factor. And by the way, people keep saying dampening factor. That's not what it is. It's like people who say asymptote and not asymptote. So 1 minus D over 4 plus D. Now the incoming edges for D is not A, it's B, so 0.25. That's the page rank of B divided by 2 plus 0.25. This is for page rank of C, just divided by 1. So we pop that into the calculator and we get 0.3375. And now the page rank of A2, which is the one we're after, is 0.3 divided by 4 plus 0.7. It's the page rank of D, which was 0.3375 divided by 3. which equals 0.15375 or 0.15 to 2 decimal places as required. If you're interested, the answers, if you did work out all the others and you want to go, "Ooh, I was right," or you might see that you got them a bit wrong for one of them, 0.30833, and this one we know is 0.3375. Those are all the page ranks for row 1, which I think is what most people would probably have done, but note that we can be a little bit sneaky. Okay, let's answer the questions on this. If the damping factor was increased, would you expect the page rank of A to increase or decrease? Well, A has no nodes going to it, only the node D. So A is really relying on those random jumps. And the higher the damping factor, the lower the random jumps. So that's what we should have written. And the next one, hopefully it sort of follows from this. Well, if we want A to be very high, we want no damping factor. We want all random jumps. And if it's all random jumps, everything is just 0.25. Okie dokie. Try this one. It's clear from marking these. Some people don't try writing their algorithms. And if you're one of those people, do pause and watch now. And if you wrote it on the day and thought, oh, that wasn't very good, spend a good bit of time trying it again now. Now here, I think, is the best answer. With recursion, the first thing we think about is our base case. So if our list has one item, we're just going to return that item. And then what we've done in the second 2 lines, we take the first item and we remove it and we return the largest of either the first item or, oh, goodness me, I've done that wrong, haven't I? Find largest numbers. Whoops. Okay, some common faults that happened here. Some people wrote algorithms that had like a current max defined outside the algorithm. Absolutely not. Okay, and some people tried using like default parameters here as well. That's really not what we want. Okay, if you find this is a downside if you use Python, which is quite similar to pseudocode, but it's easy to get too Pythony. So, I mean, if you think about it, a default parameter is probably somewhat platform specific. And anyway, we want to avoid using parameters or variables outside of functions. Now, so that's one mistake. Another mistake here is that, and you may or may not have found this was allowed, if you have a list of one item, you need to return the item, not the list with one item in it. Otherwise, you're returning a list with one item, not a single item, which you may have found when you're writing programs is causes problems. And the other mistake is going a bit over the board with the base cases, like defining 2 or 3 or 4, when really there should only be 1 in this case. Okay, sometimes that wouldn't actually cause you a problem, but maybe it did. Okay, try these. Ready? And here we go. Let's talk through them. I imagine this one, was done pretty well, making sure that we are normally, I mean, the question didn't say should you return true or false, or should you return that element, and I think I saw people return numbers which were used later, so that was allowed. I think when you're doing school tests and things, if you answer the question in a sensible manner in line with the course, then you should get the marks, even if it's not what the teacher intended. That's not a license to go completely off piste, but a principle. Now let's look at the bottom left here. We go define the function. We've made a new list, and then for each item in my list, I think I was going to do something else. I think that's why that was there. Let's get rid of that. For each item in my list, we remove the item, and then we check to see if there is an item still there, and if not, then we add it back to my list. So this is an approach I've seen. It's okay, but it's very dangerous to change the thing that you are iterating over inside a loop. So, because what will happen is we would take it out from one bit and we don't know it's going back to the same spot, in which case we might end up iterating over it again, which may or may not cause a problem. So that is the comment I've made down here. What was better, this is obviously what I was thinking of when I put that new list comment, is we make a new list, and then for each item in my list, If that item isn't already in the new list, then we add it to the new list. Now these last bits, the algorithm says removes any duplicate items from a list. It doesn't say return that list. It usually would, but because it didn't, then we can either make sure that we put new list back into where my list was, or we return new list. Okay. This was quite straightforward. The only problem is some people often use the wrong words here. So if it's a stack, we are always using peek, pop, and push. If it's a set, append or add is okay. I don't think we're as strict with set. Try this one. I mean, we've got 1 mark here, so it probably could have been more. These would be the best ideas to get across. We want to say something like if the cycles exist or if the graph is undirected. Because when a graph is undirected, as far as an algorithm is concerned, it's the cycles exist. You could just go A, B, A, B, A, B. If it's a directed tree, then we don't need to worry about revisiting the same nodes because we can't possibly revisit the same nodes. Next one. Have a read, have a try, remind yourself if you already did this. So we need to find the distance from every villa to every other villa. So we really need to use Floyd-Warshall. For this kind of question, make sure you say why not to use the things you're not going to use. Okay, if it would have been, let's say, 2 marks, you would need those 2 things. Explain why you're going to use the thing and why you're not going to use the other things. So Dijkstra and Bellman-Ford only find distances from a single source. Some people say Bellman-Ford can only be used with negative edges. Now, that's not true. It obviously can be used with negative edges, and Dijkstra is often more efficient. But we don't tend to worry too much about when Dijkstra is better than Bellman-Ford. It's to do with how dense, like the edge per vertex ratio is. But key thing, Bellman-Ford can be used whenever Dijkstra can be used. Describe how he's going to use this. I should say part... Oh, it does say part A. Okay. So we would run Floyd-Warshall, we add up all the distances for each row, and we choose the row with the lowest sum. I was kind of hoping that somebody would do it this way and not say find the average, which is fine, we're just doing 1 extra operation, but because the number of things is the same, we can just skip that last line. Not a big deal, but nice if you noticed that that is an option. Okay, pause, read, etc. This was a very hard series of induction question. Note that it says here that the whole question is leading you up to construct a proof by induction that will return an optimal number of coins. The design pattern is greedy. Somewhere or other there was a question in like 1974. No, it wasn't that. It was like 2020. Who knows? That used recursion as a design pattern. Recursion is not a design pattern. The design patterns we have, it's iteration and recursion are tools that are within design patterns. So brute force is a design pattern, for example. Let's prove the base case. Again, try this and try and make sure your proof is proof, because what a lot of people would have done is said, well, if it's 0 cents, then there are no coins, so it's fine. You've got to make sure we reference the code. So we want to show that the software or the code returns the correct change for 0 cents. We know it should be 0, that's fine. And then we refer to the lines in the code to say why it would return 0 coins, which is what we were looking for. The inductive hypothesis, this bit, I think was done rather badly. The algorithm returns the optimal number of coins for all values of k less than k. Sorry, for all values less than k, where k is a natural number. So this is strong induction. We are not going from k to k plus 1 for reasons that you'll see if you crack the inductive proof itself, which close to 0 people would have done, I think, which is often the way in algorithmics exams. These are very, very difficult. But remember, this is strong induction. If you're not a specialist mathematician, then you need to spend time doing a whole bunch of induction questions. And if you are, I know I would certainly be providing some strong induction maths questions to get the idea across. So if you do induction questions and you're kind of following a recipe but you don't quite get it, ask to see more questions, okay? Particularly if you're aiming for the top mark. If you're, if you've done algorithmics up to now and you're like, this is fun, but it's hard, I'll be happy with 25, 30, induction is probably not where to spend your time. Try and get it, but don't stray it. If you're after 40 plus, then you need to be in with a good chance of doing well on induction. Proof by contradiction. These are always quite easy to get the first line. So not impossible to get wrong, but we first off assume that a combination of 25 cents can be made without using the 25-cent coin. Now next bit is quite subtle, so I would have been generous with the second mark, but the third mark, very, very hard to get. So we know that if that combination doesn't use the 25-cent coin, it must use at least 3 coins. And the maximum amount we can make with 3 coins is 30 cents. So for those 3 coins, we're going to consider how many coins do we need for each combination. Well, it's either 10 plus 10 plus 5 plus some 1s, which we could always replace the 10, 10, 5 with 125 to make it better. Or it could be 3 10s, which we could replace with a 25 and a 5, which for some reason I've said, no, well, that's better as well, isn't it? So that means any combination, and we also know that any combination greater than 30 is going to contain that subset. So, and it's this idea of saying, well, this is the number of coins we've got. We must have at least 3, and considering all the possibilities for those 3 coins, and the 25-cent coin always makes things better. That's really, really subtle, but that's the way it goes sometimes. So it means that any number, we always want to have the 25-cent coin, or rather, if we use the 25-cent coin for any combination of at least 25 cents, we are going to get a solution at least as good as the best solution. Okay. Now, technically, we should have then proved the same thing for 10 and 5, but it just seemed like overkill. So now when we complete the proof by induction, I'll just pause. We would go back to this idea of strong induction. So we're not going to the previous one solution. Remember, the inductive hypothesis went to everything less than k. We now consider the amount k. We know that it must include the largest coin less than or equal to k. So we remove that coin and we're left with an amount less than k. And by hypothesis, we know that that amount, whether it's 25 less or it would be like 24 less or 9 less or 4 less, is going to include that amount. Therefore, the algorithm is going to work. This approach is going to work using mathematical induction. Now, the final bit a lot of people would have got right. If we just find a counterexample where the algorithm does not work, then, if the algorithm doesn't work, the proof can't work because the proof method is right, so it would be wrong. And if you try and do the same proof, and it's that idea of the 3 coins, all the different combinations, etc., that's what you'll see how it fails with this one. I'm not going to go into it now because it's a bit niche. So yeah, if the algorithm doesn't work, the proof cannot be correct. We wouldn't be able to say, well, they're not multiples of each other. I mean, it sort of feels to do with that 1 goes into 5, goes into 10, and well, 10 doesn't go into 25, but yeah. We get a sense that the first set of coins works, and we can see why these ones do not. Finally, so I'd be looking for 2 marks. I'd be looking for these 2 things: find all combination of coins that can make the amount required. That bit's kind of obvious, and then choose the combination with the lowest number of coins. If it was more marks, I'd be thinking I'd want to go into a little bit more detail about how to choose those combinations. So we would be like successively adding each coin, maybe do like a tree or something like that to choose the number of coins to make that combination. But for 2 marks, this would probably have been enough. Okay, hope that's useful. Happy revising.